All right, welcome to the Explainer. Today, we're going to crack the code on a piece of tech you use literally every single day, and you probably don't even think about it. We're talking about the algorithm that silently fixes your typos and powers some of the smartest software on the planet. So let's just dive right in. Have you ever wondered, how does your computer know what you meant to type when you make a typo? Or let's think bigger. How can software tell how similar two whole documents are? It's not magic, I promise. It's just some really, really clever logic. Okay, so this whole thing starts with a core problem. How do we figure out how similar two pieces of text are? And this isn't just about typos, you know? This idea is, well, it's a huge deal in computer science. Solving it opens the door to some incredibly important stuff. I mean, just think about it. This one single idea is the engine behind software that catches plagiarism in schools. It's what lets programmers see exactly what's changed between different versions of their code. And yeah, it's how search engines can still give you what you want, even when you spell something wrong. So to get this done, computer scientists had to, well, they had to think outside the box. They came up with this really smart way to mathematically measure the distance between two strings of text. Super simple idea, right? A small distance means they're really similar. A big distance, they're not. And that measurement has a name. It's called edit distance. It's basically a score. It tells you how much work you have to do to turn one word, or even a whole document, into another. And the key thing here, the goal, is to find the absolute minimum number of changes. Right, so think of it like a game with some really simple rules. You only get 3 moves. That's it. You can either insert a new letter, delete a letter, or substitute one letter for another. And the whole point of the game is to figure out the shortest possible path, the fewest moves, to get from what you typed to what you meant. Okay, so we've got the rules. Sounds easy enough, right? But how do you actually find that minimum number of edits? Well, the most obvious way you'd think to do it, just trying everything, what we call brute force, it runs headfirst into a giant show-stopping problem. Yeah, trying to just brute force it by exploring every single possible path? The source material puts it perfectly. It's impossibly inefficient. I mean, the number of possibilities just explodes. For anything more than just a tiny word, your computer would be stuck thinking about it for, well, basically forever. And here's the reason it's so bad. A simple, naive approach would try to match the first letters, then it would just do the same thing for the rest of the words. But here's the fatal flaw. It has no memory. It ends up solving the exact same little mini problems, like what's the distance between the letters AT and AR, over and over and over again. It's just a huge, colossal waste of time. You know, to really get a grip on why this is so inefficient, let's look at a classic math problem that has the exact same issue. You probably remember this one from school. So you're trying to calculate a Fibonacci number using that recursive method. You get this crazy branching tree of calculations. To get f of 7, you need f of 6 and f of 5. Okay, but to get f of 6, you also need f of 5. You can already see where this is going, right? And this is what illustrates the problem so perfectly. Look at this. In the process of finding just f of 7, you wind up calculating f of 4 3 different times, and f of 3 gets calculated 5 times. All this repeated work just grinds the whole thing to a halt, and it gets exponentially worse the bigger the numbers get. This is the exact same trap our edit distance algorithm fell into. Okay, so if doing the same calculation over and over is the big problem, what's the solution? Thankfully, there is an incredibly elegant and, frankly, powerful way to fix this. It really all comes down to one simple, powerful question. Why would you ever solve the same problem twice? It just doesn't make sense. If you've already figured something out, you should just remember the answer. And that's the solution. It's a famous technique in computer science called dynamic programming. The main idea is just beautifully simple. You figure out each little piece of the puzzle exactly one time, and then you save that answer so you can just look it up later instead of doing all the work again. Yeah, you can honestly just think of it like creating a cheat sheet for yourself as you go. You solve a small part of the problem, you write the answer down. The next time you need it, you don't recalculate it. You just look it up on your sheet. No more wasted effort. It's that simple. And this is what that cheat sheet looks like in practice. So to get the distance between cat and car, the algorithm builds this grid. It starts at the top left and fills it out cell by cell. Each number is just the minimum edits needed to get from a piece of the first word to a piece of the second. So you see that 0 where C and C line up? That means 0 edits needed. Perfect. The algorithm then cleverly reuses those previous answers to fill in the next cells, all the way until it gets to the bottom right corner. And that final number, in this case 1, that's our answer. The edit distance is 1. Okay, let's zoom out and bring this all home. This really clever trick of remembering your work, it's not just some neat programming puzzle. It has a massive, massive impact on the technology we all use every single day. Because it solves each little problem only once, this technique is what makes all those things we talked about not just possible, but incredibly fast. Your spell checker, that's dynamic programming. The plagiarism software, yep. Those programming tools like Git that show you what changed, you got it. And even search engines that understand you despite your typos, it's all powered by this one fundamental idea. And what's so cool is that this is a super flexible idea. The same exact logic can be used on entire words instead of just letters. And that's how a search engine can figure out that two different articles are actually about the same topic, even if they use completely different sentences. So this leaves us with a pretty cool final thought to chew on. The core idea here is so simple, right? Don't solve the same problem twice. So, what other huge, seemingly impossible problems out there could we crack just by applying that simple, powerful principle of remembering our work?